Solids, lecture number 12. So we've talked already about gases in the previous semester. We've talked about liquids briefly in this chapter. We're going to finish talking about solids, or at least start talking about solids here. We can talk about the solid state as having two basic categories. We can have a crystalline solid, which has a definite shape due to an orderly arrangement of the particles within that crystal, or an amorphous solid that lacks an orderly arrangement, and therefore have a poorly defined shape. Right? So what we're going to focus on actually here is this crystalline solids, or the solids that form a crystal, some ordered arrangement. So we're going to look at several different possible orders and how that affects the shapes. And so first let's start talking about a crystal. A crystal is just composed particles packed in an orderly three-dimensional array, and this array we call a crystal lattice. So the way that the simplest sort of repeating unit is the whole crystal is the crystal lattice. The simple repeating unit is what we call a unit cell. So we're just going to repeat that unit over a wide area to get our crystals. And all of these sort of crystals that we're going to talk about are dependent on the way we can stack these atoms together. And there's three basic ways that we can stack these crystals, or these atoms. We can stack them one on top of each other, like you see here, where one atom is directly above the other. Right? This is called the simple cubic stacking. Right? It's going to give us a simple cubic square, or unit cell, which we'll talk more about in a second. But this is a fairly ineffective method of stacking material. It's only 52% packing efficiency or whatever. So only 52% of this unit cell is occupied by atoms. The other 48 is empty space. Another way we can do it is have one layer of atoms, and then in the holes on top of that another layer, and then we can sort of stack a third one on top of that. Right? So now that this middle layer is sort of sitting in the pocket that taken up by the ones above and below. This is sort of, we see this all the time when we're stacking round objects. We can put that one of them sort of sits in the hole created by the other. This is what we refer to as AB packing order, which gives us a higher packing efficiency. 68% of this structure is now solid material, where only 32%, 32%, is empty space. And this is going to lead to what we call a body-centered cubic lattice. So let's look at these two, based on these two arrangements, these two possible crystal lattices. So we'll start with this simple cubic unit cell. We can see that at the corners of this sort of box we have these atoms. So the atoms are placed in the corner, which is going to give us, in the space-filled model here on the side, where we have these atoms, if we look at the unit cell, we cut that off into the box, this cell, we can see that though each atom is sort of sharing itself between 8 different cube lattices or unit cells, so that within this box only about 1/8 of that atom is present. So within this box that we created, we can see that there's the equivalent of one atom, because each of the corner locations represents 1/8 of the atom. There's 8 of those corners. It gives us one unit cell. And we can see also that if we look at the nearest neighbors from each one of these atoms, locations, based on this graph here, we see that it shares 6 closest neighbors. So this is what we call 6 coordinate, because there are 6 atoms near it in this crystal. Right? So the simple cubic has a lot of empty space. There's only one atom within that, because each of the corners represents 1/8, 8 corners, one sort of atom within there. But it gives us a 6 coordinate sort of complex. The other one that we talked about is this body-centered. Now we see that we have a complete atom surrounded by other atoms in this crystal or unit cell. Again, the corners are going to represent 1/8, 8 corners, that gives us 1, plus the one that's completely encased, that gives us 2. So in the body-centered, this represents 2 atoms within it. Now, if we look at the coordination, we see that we have 1 in the middle. If we look around it, each atom in this sort of three-dimensional representation is surrounded by 8 other atoms, so it's going to have a coordination number of 8. And this sort of, both of these are going to lead to fairly rectangular crystal structures in the three-dimensional or the macro state, sort of square or rectangular arrangements. If we look at another possible way, we can still do the same stacking where we have A, B, A, B, but if now we rotate the unit cell to go between what we call a hexagonal arrangement, we're going to now get what we call a face-centered crystal lattice. Or we can put another one on top of this second layer, which fills in the holes of that one, which would be, again, not exactly the same arrangement, which would be an ABC arrangement. Again, if we do that, draw sort of the repeating lattice there, we get also get a face-centered cubic or unit cell. So if we look at this third type of unit cell, with it face-centered, again, we see now that on the face of each one of those surfaces of the cube, we've completely bisected an atom. So we get inside each one of those faces, the molecule's cut in half. There are 6 faces. 6 times 1/2 is 3. Again, we have one on the outside on the corners. There's 8 corners. That's 1/8. So we get a total in this face-centered. We have a total of 4 atoms within this unit. And now if we look at the sort of how many nearest neighbors these have, we choose one and count the atoms that are around it, we see that there are 12 atoms that are touching or very close to this atom, so it gives us a coordination number of 12. Right? So based on which one of these 3 types of unit cells that we have, we can then predict how many atoms are encased within it. Also, we can, if we know the length of these unit cells, we can do some mathematics to calculate radii. Also, if we know the number of atoms in there, we know sort of the radius of those atoms, we can then calculate densities. So all of these of these solids is based on our understanding of this unit cell, which in the crystal itself is just repeated over and over and over again. Right? So we can talk about various types of these crystalline solids. We can see that we have the atomic solids, which consist of individual atoms held together by dispersion forces. Right? So if we take those things that only have dispersion forces, get them to form a solid, they're going to have what we call atomic solids. We can do the same thing with molecules, which we would then call a molecular solid. Again, individual atoms held together in the solid state by a combination of intermolecular forces. We can have ionic solids, which is a regular array of these cations and anions. Once they form, sort of solidify in the solid, those are called ionic solids. Metallic solids are those metals that form in the crystalline structure an organized value. Or we can have a network covalent, where the atoms in these crystals are covalently bonded together in sort of a 3-dimensional arrangement. So we can talk about atomic solids. It would be something like, we'll see those in a minute. The network solids, we can talk about graphite versus diamond as examples of those. So here are 2. The first one is this atomic solid where we have argon. If we can get argon to form a solid, we get this with a face-centered crystal or unit cell. We can do the same thing with methane. Again, the whole methane molecule then is the dots here, also becomes a face-centered unit cell. So this is, again, atomic versus molecular unit or crystals. an example of ionic. There's three that we're going to look at here. The first one is sodium chloride, or the rock salt crystal lattice, where the anion, the chlorines, are sort of forming the major outside, and then these chlorines are sitting in the holes that are left by this sodium, which gives us this unit cell, which you can see the space filling located there. Right? But again, it's the empirical formula is going to be the sodium to chlorine is in a 1-to-1 relationship. Another example is the zinc blend, where we take now, or I guess still, the sulfur are representing the corners of this ion, and then this unit in the holes that are left, we have this zinc 2+, which is going to give us this unit cell. Again, the shown here is a little bigger just to show you more clarity. And the last one is the fluoride. Well, now it's the opposite. The cation is showing are the corners, and the anion are located in the holes. All right. Again, so we're going to end up with a unit cell that looks like this. Within the unit cell, it's going to have that same empirical formula that we've talked about before, based on the match of charge, but it's going to give us a different crystal structure. Right? Just to be aware of those. A couple of examples of crystal metal solids. We can have copper versus magnesium. Copper adopts what we call a cubic close pack, which gives us a face-centered arrangement. The magnesium does a hexagonal close packing, which is that ABC close packing, which gives us also a face-centered, or a slightly face-centered crystal arrangement. Right? And then we said the network solids are those covalently bound complexes or crystals such as diamond or graphite. Right? So we're going to actually look a little more detail in class with these and do some calculations of density and atomic radii based on these regular repeating unit cells.
Dad, I done did it.